This spiral is not proof of an ancient law of beauty. Euclid described the ratio around 300 BCE and never called it golden. Martin Ohm attached that word in 1835. The mathematics is ancient. The beauty story is not. And in 1992, a mathematics paper showed that many of its famous examples do not hold. So why does the claim keep returning after the evidence breaks it? Start with what Euclid actually wrote. Book 6, Definition 3. A straight line is cut in extreme and mean ratio when the whole line is to the greater segment, as the greater segment is to the lesser. That is the definition, all of it. There is no name in it. There is no decimal value in it. There is not one word about beauty or art or the human body or the universe. It is a construction, and Euclid puts it to work in Book 13 to build a pentagon and 2 of the 5 regular solids. That is the job it was invented to do. The word divine arrives 1,800 years later. In 1509, Luca Pacioli publishes De Divina Proportione. Leonardo da Vinci illustrated that book, and this is where almost everything you have heard about Leonardo and this ratio actually begins. He drew the solids. The record does not show him composing a single painting around the ratio. Then the word golden. Martin Ohm, 1835, second edition of a German mathematics textbook. Then the claim itself. In 1854, Adolf Zeising publishes a new theory of the proportions of the human body and argues that this one ratio is a universal law of beauty running through all of nature and all of art, realized most completely in the human form. Read the order carefully, because the order is the argument. Zeising did not measure and then conclude. He concluded and then measured. And the moment the law exists, things start fitting it. In 1855, 1 year later, Ruber publishes the claim that the Egyptian pyramids were built on the golden section. Not from Egypt, from a 19th century publication in 1855. In 1875, James Sully carries the term into English in the 9th edition of the Encyclopedia Britannica. And by 1910, an inventor named Mark Barr assigns it a Greek letter, chosen after the sculptor Phidias. Barr said later that he doubted Phidias had used the ratio at all. So the symbol on every diagram you have ever seen is a guess about a Greek sculptor made by one man in the 20th century. A universal law of beauty published in 1854 is not a mood. It is a testable claim, and somebody tested it. 10 rectangles laid out on a table. Same height, different widths. A person stands in front of them and is asked to point at the one they find most pleasing. That is the whole experiment, and it is the foundation of every claim you have ever heard that human beings are wired to prefer this proportion. Gustav Fechner ran it in the 1870s. He is not a minor figure. He is one of the founders of experimental psychology, and this is the study that gets cited. Here are his numbers. Not a summary of his numbers. His numbers. They were reported by Christopher Green in the journal Perception, Volume 24, in 1995. 10 rectangles, ranging from a square up to 2.5 times as wide as tall. 347 responses. 35% chose the golden rectangle. 35% is the number that gets quoted. Here is the number that does not. Another 20.6% chose a rectangle at 3:2. Another 20% chose one at 1.77:1. Add those 3 together. Just under 76% of every answer he collected landed on 3 different rectangles. That is not a preference. That is a spread, with one shape slightly ahead of the others. In 1974, Michael Godkiewicz found something worse than a weak result, and Green's 1995 review in Perception reports it. He showed the result moves. The golden rectangle's advantage depends on where it sits inside the range of shapes you present. Put it in the middle and averaging lifts it. Shift the range and the advantage goes somewhere else. The finding was never about the shape. It was about the middle of the list. Holger Höge ran close replications of Fechner and published them in Empirical Studies of the Arts in 1995 and again in 1997. He did not find the preference. Now the honest part, because this is where most debunks overreach. Green's 1995 review does not conclude that nothing is there. It concludes that there appear to be real psychological effects associated with the golden section, but that they are relatively sensitive to careless methodological practices. That is the actual state of the field. Not proved false, never reliably replicated. Those are different sentences, and only one of them is true. So the aesthetics do not hold up, which leaves the mathematics. And the mathematics was never in question. Proof sequence. The following 4 visuals are held uniformly in register C by design. They walk one continuous construction, and the visual consistency is what marks them as a single argument rather than 4 separate images. Everything so far has been about what people said. None of it touches the mathematics, and the mathematics is exact. So let us be exact. What is a golden spiral precisely? It is not a spiral that looks a certain way. It is a spiral with a specific growth rate. Every quarter turn it makes, it multiplies its distance from the center by 1.618. That sounds modest. Follow it through. 4 quarter turns make 1 complete turn. So a golden spiral, after 1 full revolution, is 6.854 times further from its center than where it started. Not 1.618 times, 6.854 times. That is a violent rate of growth. It is what a golden spiral is. Anything growing more slowly than that is not one, and no amount of overlay changes it. Now the shell, the most reproduced example of this ratio in the world. Falbo measured real shells and published the result in the College Mathematics Journal, Volume 36, in 2005. The shells he measured do not grow at the golden rate. A nautilus grows by about 3 per full turn. Set that beside what the definition requires. 6.854 per full turn against about 3. This is not a near miss. This is not a measurement that needs a better instrument. It is a different curve entirely. And the shell is not the fraud here. A nautilus grows a genuine logarithmic spiral, one of the most elegant forms in nature. What was attached to it was a number it never had. So the most famous example fails, and it fails by more than a factor of 2, which raises something harder than whether one shell matches. Is this ratio real anywhere at all? The useful thing about this number is not that it is beautiful. It is that it is badly behaved. An irrational number is one no fraction can ever land on exactly, however large you allow the 2 whole numbers to be. But every irrational number can be approximated by fractions. That is what a decimal expansion is doing. Some numbers surrender quickly. Pi is famously close to 22/7 and closer still to 355 over 113. A few small whole numbers, and you are almost exactly there. There is a standard way of measuring how easily a number gives itself up to fractions. You write it as a continued fraction, a nested stack of divisions, and the size of the terms tells you how fast the approximations close in. Large terms mean fast convergence. A number with a big term early on is easy to pin down. Proof sequence. The following 4 visuals are held uniformly in register C by design. They walk one continuous construction from the continued fraction to the packing result. Write this ratio as a continued fraction, and every single term is a 1. The smallest value possible, all the way down, forever. There is no large term anywhere in it to grab onto, which makes it, in a strict and defined sense, the hardest number in existence to approximate with a simple fraction. Mathematicians call it the most irrational number, and that is not poetry. It is a ranking, and this number is at the top of it. Now ask what that is worth to something alive. A growing plant puts out each new unit at a fixed angle from the last one. If that angle is a simple fraction of a full turn, the units line up. A third of a turn gives you 3 arms and a lot of wasted space between them. A quarter gives you 4. Every simple fraction produces spokes and gaps. The only way to avoid lining up is to use an angle that no simple fraction can get close to, which is this one. The angle works out to roughly 137.5 degrees, and it fills the head evenly because it is the angle that fails hardest to repeat. A previous video on this channel showed that the packing in a sunflower head is forced. This is the reason underneath that result. The plant is not counting, it is not measuring, it is failing to repeat, and this ratio is what failing to repeat looks like when you write it down. So it is real in the seed head and invented in the temple. And the temple half of that was taken apart in print by a mathematician in 1992. That is the strange part. Not that the claim was wrong, that it was formally taken apart in a mathematics journal 34 years ago, and nothing happened. 1992, 34 years ago. George Markowsky published a paper in the College Mathematics Journal, Volume 23, called Misconceptions About the Golden Ratio. It runs from page 2 to page 19, and it is not a polemic. It is an audit. He took the famous cases one at a time. The Parthenon, the Great Pyramid, the proportions attributed to Da Vinci, the human body, and he did the one thing almost nobody bothers with. He fixed a tolerance in advance and asked whether the measurements actually fall inside it. That single decision is what does the damage. Once you say how close counts as a hit before you start measuring, most of the famous cases stop qualifying. Widen the tolerance enough and everything is a hit. That is precisely why the tolerance has to be fixed first. So the claim had a proper autopsy in a mainstream mathematics journal, with the methods stated openly. Now the record of what happened afterwards. In 2003, Dan Brown published the Da Vinci Code, which put the ratio in front of tens of millions of readers as a key to a hidden pattern in art. And the claim was installed again for an entire generation who had never heard of a 1992 audit. Before that, in 1959, a Disney film had already carried the Parthenon and the human body claims into school screenings for decades. Notice what the record does not contain. It does not contain anyone deciding to keep this alive. There is no campaign. Nobody had to promote it. It was simply easier to repeat than to check. Which means the work is not being done by a person. It is being done by the claim itself. And when you take the claim apart, there are 4 separate things holding it up. The first one is measurement freedom, and it is arithmetic rather than psychology. Take any complicated object, a building, a face, a shell, a painting. Now count the pairs of points you could measure between. Not the sensible ones. All of them. It runs into the thousands. Now note where 1.618 sits. It is not an exotic value. It sits in the middle of the band where ordinary ratios of ordinary objects land, between 1 and 2. Allow a couple of % either side and call that close enough, and a hit is not likely. It is guaranteed. You will find this ratio in anything, given enough endpoints and a soft enough tolerance. That is why Markowsky fixed his tolerance before measuring, and it is why almost no enthusiast does. The second is the free ride, and it is the reason the correction never quite lands. This ratio is genuinely real in some places. You saw one of them. That is not a concession, it is a fact, and it is exactly what makes the invented cases so durable. Every true appearance vouches for the false ones. A person who has just watched a sunflower head fill evenly has no reason to doubt the Parthenon. because it feels like the same claim. Look at where Zeising started. He started from plants, from a real observation about how growth arranges itself. And then he took that true thing and stretched it across all of nature and all of art and the human body. The false claim was not built next to the true one. It was built out of it. The third is what the two versions actually offer you. The myth offers a universe with a signature in it. Something non-arbitrary, running under the surface of shells and faces and temples. And you can see it once someone shows you where to look. The correction offers you a subtraction. It takes the temple back and hands you a tolerance calculation. One of those is worth telling someone at dinner. The other is not. That asymmetry is not a flaw in anyone's character. It is just what the two claims are made of. The fourth is the one this video started with, and it is the quietest of the four. Every retelling adds age. The name is 1835. The law of beauty is 1854. The English term is 1875. The symbol is around 1910. And the story is told, every single time, as something ancient and Greek, old reads as true. A claim that has survived 2,000 years must have been checked by somebody. Except this one has not survived 2,000 years. It has survived about 170, and it borrowed the rest. 4 mechanisms: measurement freedom, the free ride, the meaning trade, and borrowed age. And here is what makes them dangerous together. They are independent. Remove any one, and the other 3 still hold the claim up. 3 of those 4 are history. One of them you can watch happening. It is happening to the shell right now. Proof sequence. The following 4 visuals are held uniformly in register C by design. They walk the growth rate arithmetic through to the reformulated claim. Hold the 2 numbers from earlier. A golden spiral grows 6.854 times per full turn. A real nautilus grows by about 3. The measurements are published. Anyone can look them up. So what happened to the claim? It did not get withdrawn. It got rewritten. The version now advanced on goldennumber.net, the golden ratio site run by Gary Meisner, is that the nautilus grows by 1.618 per half turn. Not per full turn, per half turn. Sit with the arithmetic for a second before I say it. If the spiral grows by 1.618 every half turn, then over a full turn, it grows by 1.618 times 1.618, which is 2.618, and a nautilus grows by about 3 per full turn. That is much closer. Close enough to look like a match if nobody checks it carefully. I want to be precise about what I am claiming, because this is where a video like this usually overreaches. The sequence is documented. The measurements were published first. The reformulation appears afterwards. I am not telling you what anyone intended, because I do not know, and neither does anyone else asserting otherwise. But the shape of the move is worth seeing clearly. When a measurement killed the claim at one scale, the scale changed, which means a published correction is not what protects you here. So what does? Everything up to this point is either arithmetic or a dated document. What I am about to say is a generalization from one case, and one case is not a law. Here is what it actually rests on. It rests on this claim and nothing else. On one sequence, watched closely, a ratio defined without a name in 300 BCE, a word attached in 1835, a law of beauty asserted in 1854, and a monument retrofitted to it in 1855. Experiments that would not replicate, an audit published in 1992, and a reformulation arriving after the measurements that broke it. From that one sequence, here is the generalization. Some claims are shaped so that evidence cannot reach them, not because they are defended, but because they are built with enough freedom in them to absorb any particular refutation and keep going. That is a pattern I am inferring from a single case. It is not a theorem. It is not a measurement. And I have not tested it against other beliefs. It might turn out to be a general feature of how ideas survive. This video does not establish that, and I am not going to pretend it does. So, back to the question this started with. Why does the claim keep returning after the evidence breaks it? It did not survive because nobody checked. It survived because it is built so that checking it costs more than repeating it. The endpoints are free, the tolerance is soft. The real cases vouch for the invented ones, and the whole thing arrives wearing 2,000 years it never had. Which brings me to the only part of this you can actually use, and you can use it tonight. Take one golden ratio claim you already half believe. Anyone. Then run 3 questions at it. 1. Endpoints. Who chose where to measure from, and 2. Then measure 2 other reasonable pairs on the same object yourself and write down what you get. 2. Tolerance. How close counted as a hit? And how many measurements were taken before this one was reported? 3. Order. Did the claim exist before the measurement? Or did the measurement go looking for the claim? Find the date of each. Run the Parthenon through it. Chosen endpoints, elastic tolerance, and a claim born about 23 centuries after the building went up. It fails all 3. Now run the sunflower through the same 3. The structure is fixed, so the endpoints are not yours to choose. The tolerance is tight. The measurement came before the claim, and there is a mechanism underneath it that explains why the angle has to be what it is. It survives all 3. That is the difference, and it took about 4 minutes to establish. The check does not take the wonder away from you. It is the thing that earns it. Once you can tell a forced structure from a retrofitted one, the forced ones stop being decoration and start being evidence. If you want the other end of that scale, where nothing is left to choose and the answer is forced completely. The video on why there can never be a 6th Platonic solid is the one to watch next. Subscribe to Immutable Mechanics